Hello, welcome back. This is the first in the series of analytical chemistry videos which I'm putting together. This one, what we're tackling today is nuclear magnetic resonance spectroscopy, or NMR. Yes, I am aware of what that abbreviation sounds like. Not really much I can do about it. It is one of the most powerful techniques for determining the exact structure of an organic molecule. How powerful is it? Well, it's powerful and rare. It costs about $1.1 million for an NMR machine, and when you get it imported, you actually have to get a police escort to travel it because of the sheer radioactive force of the contents of the machine. So there's a wild fact to kick this one off. But yes, it is the most powerful technique for determining the exact structure of an organic molecule. The knowledge that we gain from it can be used to work out any molecule at all. How? We're going to talk about that. Alright, so a form of NMR is called magnetic resonance imaging, MRI. It's used in medicine to provide a highly detailed picture of anatomical features without using harmful X-ray radiation. One of the things about getting an MRI that nobody tells you is the MRI turns your entire body magnetic. Just for the briefest point, turns your entire body magnetic by passing a giant current through a magnet, and then it turns the magnet off. And then in that brief second, or brief period of time, all your cells stop being magnetic, but they give off a little energy signature. And that energy signature allows the MRI to detect and see this image inside your body. If you didn't know that, your brain's probably going, whoa, by now. NMR uses electromagnetic radiation in the radio frequency to obtain information about the structure of molecules. A lot of these are things that we play with in chemistry. You won't ever truly play with X-rays unless you go to uni and you have to do X-ray crystallography. Ultraviolet is something that we use in AAS, which we're going to cover later. Visible, well, not so much. Infrared, if you have randomly stumbled upon this video in your search on YouTube, I covered infrared in class last week, but I'm going to eventually do a video on it. And there's also radio waves. So radio waves is where NMR resides. So the energy of radio waves is so low, it won't cause electrons to be excited or change vibrational energy levels or bonds, but it changes nuclear spin state. Now, like I said, this is essentially what happens when things become magnetic. All of these little arrows are actually electrons. And this is the blue arrows represent what they look like when they're not excited, but the red arrows are what they look like when they're highly energetic. Their spin just completely changes direction. All the electrons become aligned and they become magnetic. So one of the things that we need to talk about is the fact that it changes nuclear spin state of atoms with an odd number of protons and or neutrons. Just this brief detour. When we talk about things having a magnetic property to them, what that means is electrons spin. Now, if you are encountering this video, you've probably learned about electrons having a negative force. Now, electrons having a negative force means they exert that force in the direction of their spin. But electrons are very rarely ever alone. They actually have another electron which spins the opposite direction to them. These pairs of electrons cancel the force out between the two electrons, and that means things are non-magnetic. However, when your electrons are spinning, but they don't have a pair, this generates a force, aka a low-level magnetic field. Going any further beyond this is beyond the reach of VCE chemistry, but I thought you might want to know. Now, NMR does tend to be 1H, 13C, and 31P, which we'll get to in a second, but this is only really what we do. Could it apply to anything else with an odd number of protons and or neutrons? Absolutely. So, atoms with an odd number of nuclear particles have nuclei which behave like tiny magnets. Now, if it's got an odd mass number like hydrogen, it exerts a force because it doesn't have a spin to pair. Now, a non-magnetic thing such as carbon-12, all the electrons are paired, so there's no overall force. Now, in the presence of an external magnetic field, the nuclei of each molecule will spin in the same direction. They'll either align with the field or against the field. This is lower energy or higher energy. Now, these are basically what you can think of all the atoms before you put them in an NMR or an MRI. But when you put them in an MRI, they all start to spin the same direction. It's like, whoa, man. Another image describing the same thing. They all point one of two different ways instead of just pointing randomly. The point of this is, in a magnetic field, all atoms become aligned if they have an odd number of protons and neutrons. When inside an NMR spectrometer, the nuclei are more often in a low energy state, and a radio transmitter is used to provide energy to flip the nuclei into a high energy state. So here, low energy becomes a high energy, and then because an atom cannot stay excited forever, when it releases the energy, it flips back. This is a very fancy way of explaining it using an electromagnet, but still the same thing. Low energy, high energy once we place it in the field, and then once it flips back, it becomes low energy. So, over time, the nuclei flip back into a lower energy spin and release a pulse of energy to do so. This energy is measured and represented as a graph on the NMR spectrum. Here we can see ethanol. Now, it releases three separate but unique peaks. Here we've got the hydrogen from the CH3 group. We've got the hydrogen from the alcohol group, and that's 2.6. And then we have the CH2, which is about 3.8. Most of this you'll just end up ballparking anyway. So you'll notice two things. One, there is a relative strength to each of these peaks, but two, you also read the graph from right to left. This will become useful later. Now, this explains the principles of NMR spectroscopy. If you're like, I have no idea and I don't really care, feel free to skip this slide. But, so what happens is we dissolve it in a solvent that does not produce a signal. So, typical solvents are CDCl, deuterium, they're mostly just deuterium. So, based compounds. Now, the reason why we use deuterium is an isotopic form of hydrogen, and it contains 2 protons instead of 1. This means that it will not show up in proton and carbon NMR spectroscopy. Now, a glass tube using the dissolved sample is put in between 2 magnets. The magnet is turned on. This whole sample becomes magnetic, and then the magnet is turned off. The detector picks up the energy from the flip from high energy to low energy, and it sends it to the recorder. The recorder gives that information to the computer, and the computer analyzes the signals, outputs the data as an NMR spectrum. Now, Principles of NMR spectroscopy are that the difference in energy between the higher and lower energy spin states depends on the type of nucleus and the chemical environment. You are going to get absolutely sick of hearing me say the words chemical environment very fast. So, now, remembering that we read these graphs from right to left, you will start to notice certain things. Now, here we've got our alkane groups. These are just RCH. They're about 1 as the value goes. As you move to the left, all your alkane groups start to be a little higher, but that's because they're attached to things which are electrophilic, such as a benzene ring, a nitrogen, or a carbonyl group. Left again, once you get to 4, you get your halogens and your oxygens. Up here, we've also got nitrogen and oxygen. And to the left, you've got double bonds. Anytime you see double bond, anytime you get peaks in an NMR spectrum of about 5 to 7, you know it's roughly there's a double bond. Here, hydrogen, and once you get to the values of about 9 or 10, you know that you've got a peak that's probably sitting right next to an oxygen and a carbonyl group, aka an aldehyde or an acid. Now, what do you need to know from this table? Do you need to commit it to memory? Jesus Christ, no. What you just need to remember is the closer it is to an oxygen, the further left it moves. Then its double bonds are about 5 to 8, and then aldehydes or acids are 9 to 12. Now, the 2 most common types of NMR are based off 2 different nuclei. The hydrogen nucleus, which is a proton NMR, and the 13-carbon nucleus, which is a carbon-13 NMR. Now, you'll notice that whilst these 2 look very basically the same, they read from right to left and they've got certain peaks at points. The carbon one has only single points, and the hydrogen NMR has broader peaks. And it has relative peak areas as well, but we'll get to that in a minute. Okay, so each hydrogen or carbon in a different chemical environment creates a peak in the NMR spectrum, which gives the NMR information about the exact structure of an organic molecule. Now, what they've done here is they've shown you that we've got 3 different molecules. We got ethane, we got propane, we got butanone. Now, have a look at just the carbon for a second, right? Now, we have CH3 and CH3. And both of those CH3s are connected to a CH3. This means they are identical carbon environments. Each carbon environment being identical means that if I were to run this through a carbon NMR, there would only be 1 peak because it is an identical molecule. Now let's look at the hydrogens. Each CH3 group is actually identical to the other CH3 group, which means each hydrogen also has the exact same value as any other hydrogen in the spectrum. Looking at propane, let's have a look again. We have a CH3 group connected to a CH2 group on the left, and on the right, we've got a CH3 group connected to a CH2 group. Well, what can we tell? We know that we have 3 carbons, but one is a CH2 and the other one is a CH3 connected to a CH2, like the other 2 are CH3s connected to CH2s. This means that at the end of the day, both of the CH3s are identical and the CH2s. The CH2 is a separate carbon environment. So we can say we have 2 carbon environments altogether. Now, let's look at the hydrogens. Well, a CH2 is 1 hydrogen environment because both the hydrogens attached to the carbon are the same. But the CH3, well, all the hydrogens on the CH3 are the same, but they're also connected to the CH2. This affects for reasons which we'll sort of get into, but I'm going to try and not confuse you any more than I need to. Likewise, the CH3 on the right is different, is the same as the CH3 on the left, because all the hydrogens are the same and they all see a CH2 group. Looking at butadiene, well, let's have a look. We have 4 carbons. Are they separate or are they different? Well, we have this CH3 and we have the CH3 group still on both ends, but one CH3 group is connected to a carbonyl group, whereas this CH3 on the end is connected to the CH2. This means they are different carbons. The carbonyl group, there's only one carbonyl group in the molecule, meaning that that carbonyl also has to be different to the CH3 groups. And the CH2 group, well, it's got 2 hydrogens and it's connected to 2 different carbons. So that means every single carbon is different. If you're trying to tell how do I tell if a carbon is different? Look at the group, look at the molecules coming off it and see if it's identical anywhere else in the molecule. This carbon is connected to 3 hydrogens and a carbonyl group, versus this carbon is connected to 3 hydrogens and a CH2 group. It means they're different. Now, how many hydrogen environments do we have here? Well, here's the thing. We have hydrogens on blue carbon, hydrogens on green carbon, and hydrogens on red carbon. The hydrogens on the blue carbon are connected to a carbonyl group, so unless there's another CH3 connected to a carbonyl group, we can say that that's definitely one separate hydrogen environment. Green carbon has 2 hydrogens. There is nowhere else in the molecule that has 2 hydrogens connected to a carbon. We can say that's a different chemical environment. And we have 3 hydrogens connected to the red carbon, which means that it is different to the green carbon and to the blue carbon and to the black carbon. Now, it's difficult to share results using different machines as nuclei emit different frequencies of radio energy under different conditions. So what we do is we actually compare all signals to the signal from TMS, tetramethylsilane. Tetramethylsilane is a phenomenally unreactive compound. You'll see its peak every time, but it'll be very small and very far to the right at 0. We use that as the control, essentially. How many chemical environments for hydrogen are there in that molecule? It's just 1. And how many carbon environments are there? Also just 1. How many peaks would you find in a spectrum? Well, if there's only 1 hydrogen environment, you're only going to find 1. And if there's how many peaks would you find in a NMR spectrum? Also 1. Every different environment will give you a different peak. Okay, so I'm going to stop the video for a minute. I'm going to break it up. Thank you for watching part 1. Go get yourself a drink. Go take a break. Go relax. Go unwind. If you are my Year 12 students, make sure you do the Heinemann questions. But other than that, thanks for watching.